This is a photograph of the eclipse of 1919. That's 101 years ago, which propelled the scientist into stardom, making his genius renowned. That genius is Albert Einstein, and his brilliance still illuminating the progress of science today. It was due to this tiny point, an observation of a shift in the position of a star that shouldn't even be there, a proof of his theory of relativity. Observing and analyzing changes are fundamental for science. Remember that your scientific skill begins from observation skill. Then you try to articulate your observations so that you are understood by everyone with precision and accuracy. That is what we will do with science, find explanation for the things around us. This lesson will deepen the way you describe changes around you, particularly motion. There are several types of motion. For this course, our focus is projectile motion. It is a complex one, but we can tear it down to basics so that it is easier for our analysis. We will begin with some kinematics, then proceed right to one-dimensional motion in the x-axis and the y-axis, then combine the two for projectile motion, a two-dimensional motion, then conclude the lesson with some good motion problems. I chopped this lesson into chunks of less than 10 minutes. This lesson is the first part, review of kinematics. Let us begin with a problem that is key in all succeeding analysis. Which of these two objects will be able to cover more distance in 60 seconds? A car that starts from 1 meter per second and speeds up at the rate of 0.2 meter per second, or a car that moves at a uniform speed of 10 meter per second. Before we solve that problem, let us recall your previous science. What we are doing here is part of kinematics, a branch of physics or mechanics that describes motion without looking at its cause. The other branches are called dynamics and statics. We will not talk about them yet. We will simply describe motion and kinematics, and here are some descriptions that you can use. The first one is distance and displacement. The second is speed and velocity, and lastly, acceleration. These descriptions come to us as mathematical equations because they can't be science if we can't measure them. Speed average or V average is d total or distance total divided by total time. V average is the sum of the measurements of speed divided by the number of instances. Acceleration, on the other hand, is the change in speed over change in time. Then, when you combine these three equations, you can come up with these two more. The first one without time variable, while the other one without the final speed variable. Allow me to review you some of them. When we talk about distance, that is the actual length of the path. When we try to describe how fast something moves, we compare its movement in space against time. So, if it takes 10 seconds to walk this entire path, we say the speed is 10 meters in 10 seconds. So every second, that is 1 meter. So we say the speed is 1 meter per second. Now, listen carefully here because what I will say here is a key element in the success of your analysis of motion problems. This speed that we describe could be average speed, could be uniform speed, or instantaneous speed. They are indicated by these symbols. The way we write them is important because we find them in our equations. Average speed can be written this ways. You might have been used to the symbol S for speed, but please update that to V so that you can easily link the concept of vectors when we review them. V average, or V with a bar, those who took statistics, that symbol indicates the mean, which is also an average. Instantaneous speed can be written in various ways. You can make sense of the symbol by understanding that instantaneous speed is the actual speed at the moment or instant. So speed at point A is written that way. Initial speed can be v sub I, or v sub 1, or v sub o for speed at origin. That is v subscript o for speed at origin. Let us use the terms before we describe the third one. Let's start with the first scenario, where the entire length of the path is known and the travel time is also known. If we know that this is 10 meter length, is covered in 10 seconds, then we can immediately conclude that the average speed here is 1 meter per second. 10 meters in 10 seconds is 1 meter per second. Let us say we don't have any idea about the length of the path and the time it covers that length. This brings us to the second case. Distance and time are both unknown. I ask you in this example, so what is the average speed of the car? Another way to find the average speed is by actually measuring at particular points how fast the object is. Let us say we have that instrument you point to incoming vehicles to know its speed, a radar speed gun. And say we took this speed at the following points and found 0.5 meter per second at point 1, 2 meter per second at point 2, 0.5 meter per second at point 3. All these are called instantaneous speeds, and they can be written that way to distinguish them. Look at how v sub 1, v sub 2, and v sub 3 are written to convey this idea. To describe the speed as an average, we simply get the average, combine and divide by the number of instances. That is 0.5 plus 2 plus 0.5 divided by 3. This gives us 1 meter per second. Now look at this. This one is the average speed, while these ones are instantaneous speeds. I just made this example a little easier for typical situations. It is possible that you will not get 1 as an average if the object speed in our example is very erratic. Average speed must be used at a particular context. If I ask you what is the average speed of a SpaceX rocket, and you context this from the ground to the first kilometer, definitely the speed that you will find will be different if what I meant is the entire flight until it reaches its target orbit. If you would like to measure the average speed by using instantaneous speeds, your data will be more accurate as you increase the number of observations. Say, for example, have 20 measurements from points 1 to 20, get the average of the 20. Now let's take a look at this another possibility, our third case. It is also possible that the object is not changing its speed. From the beginning till the end of our observation, it maintains a speed of 1 meter per second. We are only doing this third case as an emphasis. If we measure all 4 points, we will get the same value for all instantaneous speeds. Point 1, 2, 3, 4, all 1 meter per second. If the speed is not changing, then we say the speed is a constant or it is uniform. It doesn't come as a special symbol, but it gives us a very important insight that average speed is equal to any instantaneous speed there. As I warned you earlier, distinguishing instantaneous speed and average speed, this is often the source of error in the solution because in your kinematics equation, you have average speed. You shouldn't use there instantaneous unless it is uniform motion. And vice versa, there are instantaneous speeds in your equations and do not use there the average speed unless it is uniform motion. Now the last description that we need is acceleration. An object that changes its speed is accelerating. Acceleration is a measure of how the speed is changing. This is why in your equation it says change in speed over time. Say for example, an object starts from 0, then we record its speed for every second. From 0, let us say it becomes 1 meter per second, then 2 meter per second, then 3 meter per second. By inspection, we find that the rate of change in speed, or acceleration, is 1 meter per second per second. Look at every interval of a second. The change is 1 meter per second. The triangle symbol is a Greek letter delta, which is read as change. Now, to show this as a solution, you can start with the acceleration, which is change in speed over time. In this scenario, that change is 0 to 3 meter per second over a time interval of 3 seconds. This gives us 1 meter per second, or 1 meter per second squared. Throughout the course, we will only look at this kind of acceleration that is constant. We will not yet look at situations like 0 meter per second, then 1 meter per second, then 3 meter per second, then 6 meter per second, because in there, the rate of change is also changing. That's a lot of change in a sentence. And at this point, we can only handle one. Now we have completed reviewing the basic idea among these descriptions: distance, instantaneous speed, average speed, uniform speed, and uniform acceleration. What are they for? They are for describing the motion that you see. Now the question is, can you do the math with them? Let us go back now to the question from the beginning of this lesson. Which of these two objects will be able to cover more distance in 60 seconds? A car that starts from 1 meter per second and speeds up at a rate of 0.2 meter per second, or a car that moves at a uniform speed of 10 meter per second? What do you think? Do the math and be awesome by showing us how you got it. I'll post the solution later as a supplemental video titled as Part 1 Solution Kinematics Review.